Okay, let's begin. Questions on the homework? I think 8.4.
Five.
8.5?
Yeah, 8.5.
Oh, okay. Wow. Lazy. Okay. Questions?
It was the sum from 0 to n factorial times 2x minus 1 to the n.
Times 2x minus 1 to the n.
Yeah, and it's set to find the radius and
Interval of convergence. Okay, how do we do that? Ratio test. Always a ratio test. You look at the limit. Basically, we're going to set the limit of an plus 1 over an less than 1. So let's find that limit. So we have limit n plus 1 factorial 2x minus 1 to the n plus 1 divided by an, which is n factorial, times 2x minus 1 to the n. This cancels that. This cancels that. Limit as n goes to infinity.
It's infinity.
Right, so this equals infinity.
As long as x doesn't equal 1.
What does that mean?
no x values.
As long as x doesn't.
There's only one x value, meaning only converges at a point. i.e., x equals a half, right? If your x equals a half, this guy goes to 0, and then you're just summing 0, that will converge. So the radius of convergence is 0. And there's no interval of convergence. It's literally converges only for the value x equals a half, otherwise it's going to diverge. Other questions? Because the only way to force this to not be less than not go up to infinity is to kill it with a 0. Two. I assume radius of convergence again? Yeah, so same thing. We're going to find that limit. These guys you can essentially ignore because we're throwing them into absolute values anyway. So this is x to the n plus 1 over 4 to the n plus 1 ln n times, flip this guy.
In the bottom it's ln n plus 1.
Like that?
No. When you do it.
Oh, here. Yes. So this is the limit. This cancels that. This cancels that. This will go to 1 as n goes to infinity. And so basically I'm left with x over 4. Set this less than 1. This means our radius of convergence is 1. Since x over 4 is less than 1, this means that minus 4 is between x. Sorry, the radius of convergence is going to be 4. It'll be 4. Anyway, what's, do we need interval of convergence as well?
Yes.
So I have to check the endpoints. So if my x is -4, plug in -4 here, I would end up with the series of 4 to the n over 4 to the n ln n, which is just a series of 1 over ln n. What happens to that, guys? Diverges. How do we know it diverges? Right. Diverges by comparison. Right? 1 over n is less than this. We know that diverges because it's harmonic. What if x is positive 4? Then we have the sum of -1 to the n over ln n. What happens to that? Converges by alternating series testing. This means my interval of convergence is, it doesn't work at -4, but it works at +4, and my radius of convergence is 4. Right, because that comes from here. This says my x in absolute values is less than 4. That's the form for the radius of convergence.
For the second problem, x equals to 4, do we have to say how converges condition absolutely?
For our purposes here, it won't matter. Other questions? Yeah?
22, it said the sum from 0 to infinity of c sub n 4 to the n converges. And so show that a and b converge, or do a and b converge, and part A was the sum from 0 to infinity of c sub n -2 to the n. And then part B was the sum from 0 to infinity of c sub n -4 to the n.
Okay, so we're given that this converges, and do these converge? What do you think?
I think A does, because for the first one, R equals 4, so your interval is -4 to 4. And for A, -2 is within that interval. So it must converge too.
You looked at the radius of convergence?
Yeah, for the top one,
Okay, and that's going to be what?
4.
And then your idea here is the radius of convergence is 2. Like, is radius of convergence the only thing that matters still?
And the endpoints.
We need more than that.
Take the absolute value and get Cn to the n.
For this one, if I take the absolute value of Cn minus 2 to the n, I get the series of Cn 2 to the n,
Which is less than Cn for the n.
which is less than Cn 4 to the n. Yes. So it converges by comparison. Right, the radius of convergence doesn't really come into play here. The only thing where you can judge by one series and another series where the radius of convergence is a factor is if you're actually doing something like taking derivatives or integrals of that series, then the radius of convergence of the original would matter. Because you're using this series to make another series, but this is something completely different. So radius of convergence is not really where we want to take it. I'd use comparison. I'd also compare with this. Right? Because this in absolute values is exactly that. So actually both converge absolutely. Right? So we have absolute convergence. Same thing if I have the sum, if I take absolute values of Cn minus 4 to the n. That's just Cn 4 to the n, which converges. So this guy converges absolutely. Yeah, so I just use comparison. And if the negatives are a problem, just take absolute values, they go away.
The book says that
It's the question is, does it follow that A and B converge if the top one converges? But like if the top one if the top one converges, it's basically a power series of R equals 4. So that bottom B is also the power series of R equals 4, but at the endpoints, which doesn't necessarily converge.
How is it phrased? What is the question exactly? This is 23.
I don't think it's like asking you to actually necessarily solve it.
If this is convergent, does it follow the following series are convergent? Do you think like at the endpoints there would be an issue?
Well, you can't. It doesn't follow that they are convergent. It follows that they might be. I don't know.
This is minus. Oh, I see the issue here. Our Cn, we don't know if that's positive or negative, so that will be an issue. Technically, we have to worry about the sign of Cn, because that could actually change things. So, yeah, I guess we would worry about. Where's the eraser? Let's see what we can say about Cn then. It's convergent. Does it follow that this is convergent? Let's see the IOC and the ROC. See if anything happens with the Cn. So our Cn, they have to be a quarter apart. That means that 4 might give trouble. So there should be an example where for Cn where one converges but the other one doesn't. Yeah, our factor of 4 here is a problem. The other one would have a factor of 2, which is within our radius. So can you come up with an example where B doesn't converge for the Cn? You'd have to choose a Cn. think of an example?
Cn is a negative constant.
Yeah, if Cn is, give me, yeah, I feel like if Cn hits negatives and making this positive, that will be an issue. So,
Can you do test for divergence?
we could do tests for divergence. I don't really see how that would help here. Because we know that this limit goes to 0, which doesn't really tell me much about the Cn.
If you divide by 4 and times that, it becomes a harmonic series.
So something like Cn equals minus 1 to the n over n4 to the n. Forgot Cn here is a real number, so it can have negative signs, which is where that taking absolute values, our absolute convergence trick there might not work. So here, Cn4 to the n converges. By alternating series test. But Cn minus 4 to the n diverges. Because it is harmonic. Yeah, so being off by a factor of 4 was our limit here. So the first one is fine using the absolute convergence test because how much time do we have? I can take a few more questions. Did we also have 8.6?
Yeah.
We should probably start 8.6.
Yeah. Anyway.
What does that say?
I don't know the question, but
The function x over 1 plus 4x, all of that squared.
All of this squared?
Yeah, sorry, just over 4x.
It's going crazy. Like that?
Yes. Minus power circle. The function is determined of 3.
Okay, so find power series and ROC. Okay? How do you do it? Like the second to last example I did last class should sort of point you in the right direction.
The derivative of 1 over 1 plus 4x equals 1 over...
Yeah, so let's look at this function, 1 over 1 plus 4x. Notice that our g prime would be what?
Negative 1 over 1 plus 4x.
Negative 4 over 1 plus 4x squared.
Right? That sort of reminds me of this guy. My x can factor off, so I can think of this guy here as minus x over 4 times plus 4x squared. And this guy is a derivative. So basically what I'm going to do, find the power series for this guy, differentiate to get the power series for this guy, and substitute it here. So how do I find the power series for this? So far there's only like one power series that we know. So
Make it 1.
try to make it look like 1 over 1 minus x.
Make it 1 minus 4.
1 minus a minus 4x, which means you plug this into that series, 0 to infinity. Instead of x, you have minus 4x to the n. So this is 0 to infinity, minus 1 to the n, 4 to the n, x to the n. All right, that's the power series for this guy, which means that minus 4 over 1 plus 4x squared is equal to the derivative of this guy. With respect to x, so I'm going to bring the power down, subtract from the power, and that's my power series for this guy. So I have enough space. So this means my x over 1 plus 4x squared is actually equal to minus x over 4 times this series. Which means I can bring this minus in, so this is just the series from 0 to infinity of minus 1 to the n plus 1 by multiplying the negative 1 times this. Put the 4 inside, dividing by 4, I get n times 4 to the n minus 1. The x multiplies here, bumps up the power, so that gives me x to the n. So that's my power series.
Come on, you lost me at negative x over 4.
Yeah, I don't know if I got that one. I mean, I understand like the rest of this. Didn't know where you get that. X over 4.
Well, I have x over 1 plus 4x squared, right? I want to somehow get this guy in the mix because I know I can get to that guy, right, by just differentiating this. So I just factor off an x. So this gives me 1 over this, but I don't want 1 over that. I want minus 4 over that.
Oh, okay.
So what I did was I multiplied by minus 4 over minus 4. Right? Bring this 4 to the top. This 4 I moved over there. So I have minus x over 4 times that minus 4 over 1 plus 4x. And that's where I got this. So now I know if I can find the power series for this guy, which I can because I know how to find the power series for this guy, I differentiate to find the power series for that guy. Then I multiply by minus x over 4 is going to give me the power series for this one. This sort of manipulation, very important. You're going to use it in 391 all the time. You need something and if you don't have it, just multiply and divide by it. Put it there. So that's our power series. How do we find the radius of convergence? So we know that x to the n from 0 to infinity converges where? X must be less than 1 in absolute values. Which means I'm looking at this series where I tried to plug in minus 4x to the n will converge for whatever is here should be less than 1 in absolute values, which means my x should be less than a quarter.
How do you get to the minus 4x to the n from that? Because you have n minus 1 x to the n.
No, from here.
I'm
I'm looking at this guy.
Oh, and because the radius of convergences is the same.
Yeah. So the radius of convergence for this guy is the same as his derivative. So if I know this guy, I know that guy. So that's my radius of convergence. Notice that here x is equal to a quarter in absolute values. You just get the series of either 1 or minus 1 to the n. Both will diverge, so the strict inequality remains. It'll be exactly the same radius of convergence. Okay, let's move on. I know you guys are dying to learn more about series. We'll do something really cool now.
I'm dying.
Literally dying. We're going to talk about Taylor series. And what's called the Maclaurin series. Pass up the homework. Let's make sure we finish this. Okay, let's do this. So I know you guys are saddened by the fact that you're really very limited when it comes to developing power series. I mean, if you can't make something look like 1 over 1 minus x, you're sort of stuck. Don't like the restriction, so let's sort of try to generalize this idea. How do we get to power series? Because we saw that they're important. We can use them to approximate integrals and things like that. So what if what we have doesn't look any way like 1 over 1 minus x and we can't get it to look like that? What do? Well, let's try to figure this out. Suppose f of x has a power series. Right? So pretend that we could write a power series, hypothetically. What would this mean? And so let's suppose I can write my f of x as a power series. So it's like C0. So it's from 0 to infinity of Cn x minus x naught to the n. Right? So the power series centered at x minus x naught. This will be C0 plus C1 x minus x naught plus C2 times x minus x naught squared, C3 times x minus x naught cubed, so we're supposing that we have a function that we can do this for, right? So I don't know what the function looks like or anything, but suppose it's differentiable. In fact, it's differentiable repeatedly. I can keep differentiating it repeatedly. So this would mean, let's say I differentiate this guy. What would I get? I get C1 plus 2C2 x minus x naught plus 3C3 x minus x naught squared plus 4C4 x minus x naught to the fourth to the cube, etc. Right? Now what if I evaluate f at x naught? Why? It'll kill everybody except this guy, right? Let's keep going. What's the second derivative look like? So I'm taking the differential derivative of this.
6C2
No, just be 2C2.
6C3 x minus x naught.
So 6C3 x minus x naught plus
12C4 x minus x naught squared.
Or if I evaluate that at x naught, what happens? Everyone dies except this guy. So I get 2C2. In other words, I can say my C2 is just the second derivative evaluated at x naught over 2. Let's keep going. And the third derivative, what does that look like? 6C3 plus 24C4 x minus x naught plus, it's going to be something else. Evaluate that at x naught. I get 6C3. In other words, I can say that my C3 is actually f triple prime at 0 divided by 6. One more time. Just in case you can't see the pattern yet. This is 6C3. We're finding the fourth derivative. So I'm going to differentiate this. I'll have 24C4 plus, I'll have something times x minus x naught plus blah blah blah. Now if I evaluate the fourth derivative at x naught, I would just have 24C4, which means my C4 I can write as the fourth derivative of x naught over 24. Now we go back to the training that we learned in 8.1 where we had sort of a sequence and we tried to figure out a pattern for that sequence. So far what do we know? Well, I know that if I evaluated the original at x naught, everyone would die except C0. So that means my C0 is f of x naught. I also just found that my C1 is f prime of x naught. My C2 is f double prime of x naught over 2. My C3 is f triple prime of x naught over 6. My C4 is f to the fourth derivative at x naught over 24. Do we see a pattern?
Yeah.
Well, notice that the subscript is the same as the number of derivatives I'm taking, right? So the C0 is from taking no derivatives, C1 comes from taking one derivative, C2 comes from taking two derivatives, C3 from three derivatives, C4 from four derivatives, etc. What other pattern is there? What about the denominators? 1, 1, 2, 6, 24. What behaves that way? Factorials. Notice that this guy here is 0 factorial. This guy here is first derivative over 1 factorial. This is the second derivative over 2 factorial. This is the third derivative over 3 factorial. This is the fourth derivative over 4 factorial. Can you give me a general formula for the Cn?
N
Has to be the nth derivative, whatever the subscript is, that's the same number of derivatives I'm taking, evaluated at x naught over what? N factorial. The subscript tells me the number of factorials I'm taking. N factorial. So it turns out if I could write a function as a power series, I would know exactly what my coefficient should look like. This means, basically, my f of x, this random function that is possible to express as a power series, I can actually write it as a sum from 0 to infinity of the nth derivative evaluated at some point over n factorial times x minus x naught to the n. This, ladies and gentlemen, is called the Taylor series. It's called centered at x naught. Basically what it does, it gives a power series for a, I don't know, random function. Can I find a Taylor series for any function? Does every function have a power series? Only the differentiable ones. And only the ones that are infinitely differentiable. Note, to obtain this, I had to be able to take derivatives. This works only if f is differentiable. Not all functions have this property, right? But many functions do, many functions that we care about. So as long as we have a function that we can keep differentiating forever, I can find a power series for that function. What are some of the nice functions that I'd like to be able to find power series for? How about sine? I can keep differentiating that forever. It means I can find a power series for it. E to the x, I can differentiate that forever. I can find a power series, right? Cosine, I differentiate that forever. I can find a power series. Let's actually do some of this. Oh, by the way, let me mention one more thing. The other guy in the title, if x equals x naught, i.e. the power series is centered at 0, then I can write f of x in this form. N goes from 0 to infinity of f to the nth derivative evaluated at 0 over n factorial times x to the n. This form has a very special name because we like evaluating at 0. This is what's called the Maclaurin series. Right, so it's basically a Taylor series centered at 0. You call it a Maclaurin series. And Taylor series is just a power series. But this guy named Taylor came up with this, so we call it a Taylor series. Whenever we're using this formula to figure out a power series for a function. Let's do an example. Find a Maclaurin series for, let's do an easy one, f of x equals e to the x. In other words, I want a power series centered at 0 for the function e to the x. What are we going to do? We're going to take a bunch of derivatives because I need to figure out this formula. I need to figure out what does the nth derivative look like. So I can plug into that formula and then I'm done. So first, what's the 0th derivative? I know f of x equals e to the x, which means f of 0 is equal to 1. How about the derivative? What's that? E to the x. Which means that f prime of 0 is f prime of 0, 1. Double prime of x is e to the x. Means that double prime of 0 is triple prime of x. This means, what do I do? The third derivative at 0 is, I don't know, what is it? 1. See a pattern? Of course.
The zero comes from being centered at 0, right?
Yes, because I said Maclaurin series. It means I'm evaluating at 0. So now, what does this mean? What's the nth derivative evaluated at 0? It's always the function 1, right? I'll keep getting 1, because derivative of e to the x is just itself, and you evaluate it at 0, you're always getting 1, which means e to the x is equal to n goes from 0 to infinity of f to the nth derivative evaluated at 0 over n factorial times x to the n. This is the Maclaurin series. But what is this guy? I just found that that guy was 1. This means that my e to the x has this power series. N goes from 0 to infinity, x to the n over n factorial. This is the power series for the exponential function. It is something you should have memorized. This is the Maclaurin series. If I'm centered at 0, that's what my power series for the exponential looks like. Functions. By the way, if you actually do the ratio test on this guy, you'll find that the ROC is infinite, right? Because you're dividing by n factorial, the limit's actually going to go to 0. And so that means you have an infinite radius of convergence. But we can get the following, right? So e to the x we just found. That's the series from 0 to infinity of x to the n over n factorial. And in fact, that converges for all real numbers. Whatever x I feel like plugging in here, I can plug it in here. It's the same as plugging it in there, right? Differentiating this is the same as differentiating that, etc., etc. So let's move on. Another function you should know, something like sine of x. If you do sine, you're going to realize that the derivative is cosine, but then the derivative of cosine is minus sine, and then you're going to have alternating signs. So this guy actually has a minus 1 to the n in it. There's going to be an x to the 2n plus 1 over 2n plus 1 factorial. This guy also converges everywhere. You can do the same thing for cosine. Keep repeatedly differentiating and plugging in 0. You will obtain minus 1 to the n x to the 2n over 2n factorial. Converges everywhere. Of course, 1 over 1 minus x is the guy we learned about last time. You can still do this sort of thing on this guy, and you'll coincide with what we knew before. This is just n equals 0 from x to the n. This one doesn't converge everywhere, though. This converges for x less than 1 in absolute values. These you have to have memorized. Right? Very important. Right? You know this now. These are synonymous. Saying sine is the same as saying that, and vice versa. Now with these we can do some pretty cool tricks, but for now let's just take that. How to use this, let's actually do an example. The realest kind of example we can do. It's actually from a previous final. Let's look at Fall 09, problem 8. Very nice example where you would use this problem. And it's likely that something like this would show up on your final. So let's actually do it. A. So a problem like this would show up in part 2. Right? You'll never see this in a part 1. In a part 1, they're definitely going to ask you about convergence tests. So they're going to say, tell us whether it's absolutely convergent, conditionally convergent, or divergent. That's going to show up in part 1. Right? Part 2, there's going to be another series question, and it's going to be on Taylor series and Maclaurin series. Right? Usually it will be a Maclaurin centered at 0, but they could tell you a Taylor series centered at some other point. Doesn't matter. It's the same process. You're just going to evaluate at that point that you're given. But if they say Maclaurin series, it means the point you're evaluating at is 0. Yeah, so here's what it says. Write down the first 3 terms of the Maclaurin series. Or sin x. E. Do the same for sine of 2x squared. C. They ask you to estimate an integral. The integral from 0 to 1 over 10 of sine of 2x squared dx. As a sum of 2 fractions. Give with explanation an upper bound for the error. So that's a possible type of problem from part 2 of a final. Give me a second to copy that down. A. So by the time you get to the final, part A should be 3 points, because this guy is just something you regurgitate from memory, right? That I know is this. By the time you hit the final, you should know that. So I know that sine x is equal to the summation from minus 1 to the n of x to the 2n plus 1 over 2n plus 1 factorial. Which means what he looks like is start plugging in n equals 0. What do I get? I get x. If I plug in n equals 1, I get x cubed over 3 factorial plus, continuing this pattern, x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9th over 9 factorial, etc. Right? So notice that the sign gives you all the odd powers of x divided by the odd factorials. Right? So this is 1 factorial. That's actually sign as a series. Continuing that pattern gives you exactly the sign function. So when they said just write down the first 3, but I just wanted to continue the pattern so we start. So your answer to this would just be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Right, you just write that down as the answer. Part B. Once you know part A, part B is also not bad. What do? Yeah, you literally just plug it in, right? Just like here, I just plugged in 2x squared into this side, but that side is exactly the same, so plug in 2x squared for x over here. So that's going to be 2x squared minus 2x squared cubed over 3 factorial plus 2x squared to the 5th over 5 factorial. Or I can write it down, simplify a little bit. This is 8x to the 6 over 3 factorial plus 2 to the 5th, 32 x to the 10 over 5 factorial. That is the answer to part B. Yeah?
Do you have different derivatives of 2x squared? And like a chain rule type thing?
Why am I taking derivatives?
Since that's the function, get the Taylor series, and you have to take a derivative of each, take each derivative, so like, would there be changes?
I'm not doing derivatives. I'm just evaluating sine at this angle. Right? Taking a derivative would mean I'm going to a cosine, but I'm not. Right? Remember, if I take derivatives, if I take a derivative of this, I have to take a derivative of that. They're equal.
And I mean, like, if you go from scratch, like, wouldn't you have to, if you make the series from scratch, wouldn't you do that?
Oh, to make the series from scratch? Well, you wouldn't. You would have it memorized. But we could make it from scratch. If you're interested, I can show you how. You would take derivatives, yes. Just as the same thing I did with the e to the x over here, you'd do that again for sine. And you'd see a pattern, and you'd end up with this. I can probably show you afterwards. But as in a final, you can just write this down. It should be something you have memorized. You'd only have to derive it if you forgot, which would be bad, but if you know how to derive it, I'll forgive you. But you'll lose like 5-10 minutes doing it from scratch. Because it has, for sine and cosine, there's a weird pattern because it skips every 4 and there's zeros in between. So it's going to be hard to see the pattern. That's why I do recommend that you look up how to derive it and try it at least once in your life. It's just something that you should do. But once you do it one time, you never want to do it again. You'll see what I'm talking about when you actually do it. All right, so yeah, this I expect you to just know. Like, you don't have to show this. Right? Just state it. Right? Once you know that, you just plug in 2x squared to get that. Right? But yes, I would derive that using a Taylor series. I can just take derivatives and evaluate them at 0. Right, so now we're moving on to part C. You need to estimate this integral. Now, one, I want you to realize that I want you to appreciate you can't actually cheat and sort of do this the short way and do final theorem calculus, because that is not integrable. We can't integrate sine of 2x squared. Has no antiderivative, right? So you can't do, this is pretty much the only way you know how to do this. So basically what we're going to do, we're approximating. So we're just saying this is something like, it's roughly equal to, going to replace this guy with his series. In fact, I'm going to replace it with the three terms that I just found there. 2x squared minus 8x to the 6th over 3 factorial plus 32x to the 10th over 10 factorial x. Now they said the sum of 2 terms, but there's a reason why I'm doing 3 terms, you'll see in a second.
Over 5 factorial.
5 factorial. Okay, how do I differentiate that? Or integrate that? 4x
Wait, no, that's a derive.
Yeah.
2/3 x cubed.
It said 4, just throw it on. X to the 7 over 7 times 3 factorial. Come on, knock the rust off your brains. Actually try. Okay, we're going to evaluate at 0 to 1 over 10. Now, I'm just going to plug in 1/10. Obviously, if I plug in 0 over 1, 0, plug in 1/10, I get 2 over 3 times 10 cubed minus 8 over 7 times 3 factorial times 10 to the 7 plus 32 over 11 times 5 factorial times 10 to the 11. So it means my answer that they actually asked me for is 2 over 3,000 minus 8 over right? That's the approximate value as the sum of 2 fractions. Yes?
Why are you raising the 10 to a power?
Because the x is to a power. I'm plugging in 1/10 into here. So it's 1/10 to the 7, which is just 1 over 10 to the 7. Same thing here, it's 1/10 to the 11th, which is 1 over 10 to the 11. 1/10 to the 3rd is 1 over 10 to the 3rd. And, right, so they asked me for 2 fractions, so I gave them the answer is 2 fractions. That's the answer. Yeah.
Can we just leave it as the one right above that, or do we have to go into
It doesn't matter. Just like
So why is it that you did 3 terms?
that's what you should be telling me. Why did I do 3 terms? I was just going to ask. The third term gives me the error. How do I know it gives me the error?
Alternating series.
It's an alternating series, which means I can apply the alternating series estimation theorem to tell me how good an approximation of 2 fractions is. The third term is going to tell me how good an approximation is the first 2 terms are. So it says here, give with explanation an upper bound for the error. By the alternating series approximation theorem, that's my explanation. The upper bound, what is that? For the error is just the absolute value of the last, the n plus first term, is the third term. Right, so the sum of the first 2 terms is approximated by the third term. The third term will tell you how far it is from the actual answer. That means the approximation is good within this much. Which is insanely great. Right? It's like 15, that's what, 20 decimals? That's a lot of decimal places. Right? Because this is 120, so you're going to get 2 decimal places from that, 1 decimal place from that, 11 from that. Yeah, so it's like, that's good up to 15 decimal places. Right, so just 2 terms here gets me within 15 decimal places of the actual answer, which is a pretty good approximation. And this is the explanation, the alternating series estimation. That's my upper bound. Since the theorem says that the an plus first, the error is less than or equal to the an plus first. Yeah. That's what the answer to this would look like. So when you're practicing this final, just forget, right? Try to do it on your own from scratch. This would be the solution. Let's do some more cool stuff with series. We have some time. Let's just have a little fun. How about you write something like ln2 as a series? Show that ln2 is actually 1 minus a half plus a third minus a fourth plus. By the way, fun fact, when you type in ln2 into your calculator, what it actually does is it treats it as a series. Then it says, how many decimal places can I use, right? Oh, I only go up to 8 decimal places. So then it uses the alternating series approximation theorem to tell itself how many terms I need to calculate to get 8 decimal place accuracy. And your calculator computes this to that many terms and gives you that answer on your output, right? So, yeah, you've been playing with series your whole life. Well, as long as you've been using calculators and computing things like ln. So it's good to be able to do this because you can actually approximate it, right? ln is irrational. Like, how do I know what that is, right? But I can write as a series, and I can know how good an approximation is by taking any amount of terms. Right? How do you show that? Ideas? I'll give you a hint. Now do we have ideas?
Differentiate.
Isn't the integral of this series like non-complex?
Yeah. Note the integral of 1 over 1 plus x dx is actually ln of 1 plus x. And if I get to get ln2, I would just plug in 1 here. So that would give me ln2. So if I want to do a definite integral, put a 1 up here. If I plug in 0, I get ln of 1, which is 0, so I can do that. And now the trick is, write this guy as a series. So basically, this would be from 0 to 1, which is actually ln2. So the idea is ln2 is equal to the integral from 0 to 1 of 1 over 1 plus x dx. This is the integral from 0 to 1 of, write that as a series, it's minus x to the n from 0 to infinity. Dx. This converges absolutely when you're on an interval of length 1. So this is just a series of the integral of minus x to the n dx. This is the series from 0 to infinity. I just integrate this. x to the n plus 1 over n plus 1. This is a series from 0 to infinity. Plug in 1 here, I just get minus 1 to the n over n plus 1. Plug in 0, I get 0. So actually ln2 is this series, and if I start writing out the terms, if I plug in n equals 0, I will get 1. Plug in n equals 1, I get minus 1 over 2. Plug in n equals 2, I get 1 over 3. Plug in n equals 3, I get minus 1 over 4, etc. So yeah, in some way, shape, or form, you type ln2 in your calculator, it does this. And then it approximates it and gives you back however many decimal places can fit on the screen. Computer algebra programs would do the same thing. MATLAB would do something similar. Mathematical would do something similar. So yeah, that's what's going on in the background. Let's look at something else we can use for a series. Write 1 over e as a sum. E. You can use this to evaluate limits. Let's use it to evaluate x approaches 0, sine x minus x over x cubed. Sure, you can do that with L'Hopital's rule by differentiating 3 times, but let's do it another way. There are going to be times when differentiation is annoying. X limit as x goes to 0 of x squared e to the x over cosine x minus 1. Maybe I should leave you guys to do that and put those out as a bonus or something. E as a sum we actually know, so remember that e to the x is the sum from 0 to infinity of x to the n, which is just 1 plus x n factorial. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. So this means e to the minus 1 is, just plug in minus 1 for x. So plug in 1 minus 1, that gives 0. Plug in minus 1 here, I get 1 over this. Minus 1 here, minus 1 over 3 factorial. Minus 1 here, plus 1 over 4 factorial. Minus 1 over 5 factorial, plus 1 over 6 factorial.
What happens to the first guy? What happens to the 1?
X is minus 1, so it kills this plus 1. Yeah. Write 1 over e in your calculator, that's what it computes. Use it as an approximation theorem to get itself to 8 or 10 decimal places. You could do something like evaluate a limit. Let's look at something like that. Sure, we could do L'Hopital's rule like 3 times. And depending on the functions, this might be a viable option for you. But let's suppose the functions were really nasty and differentiation would be annoying. If I see something like sine x minus x over x cubed, I can actually use series to help me figure this out. For example, I know what sine is as a series. sine is actually x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, etc. Minus x all over x cubed. Now what's going to happen? I have x minus x. Those guys will die. And then the cube, I can divide into each term. Right? So I'm going to basically have minus 1 over 3 factorial plus x squared over 5 factorial minus x to the 4th over 7 factorial plus x to the 6th over 9 factorial minus. Now I plug in x equals 0. Everyone's going to die except the last term, and it's minus 1/6. Do L'Hopital's rule 3 times, you'll get the same answer. The other two are similar. You can probably try those on them. Here's another one if you want to have some practice with this. Right? Like doing L'Hopital's rule on this one would be really annoying. Do product rule in the top, chain rule in the bottom. You keep differentiating over and over. Very annoying. Another one, sine x minus x. You can do all these using series. Series are used to evaluate limits more often than you think. So yeah, you can try those on your own. Each one to try. It's the same sort of manipulation. Here you're going to replace e to the x with his series, replace cosine with that series, and sort of simplify to see what you can get. Same idea here. I actually derived the series for this for you in the previous example. So you replace ln of 1 plus 4x with his series, you replace this guy with that series, this guy with that series, and do some algebraic manipulation, and you'll see that you'll get something that's easy to evaluate.
Professor, can you say what's up with me? Can you tell me like an example from the final for example?
Okay. Well, I already did one, but what example did you have in mind? Well, I don't know all the finals in my head. Someone has to give me a question. But the example would look pretty much like the example I did here, where it said, write sine of this as a power series, and then do that.
Is it always going to involve that we know those 4 or 5 ones that you gave us?
Yeah, more than likely, the vast majority of cases, they're going to ask you something with a sine, or a cosine, or an exponential, or something that was like 1 over 1 minus x. It should be something that you can figure out pretty easily. Right. What they really want to test is if you can use your knowledge to evaluate an integral and tell how good your approximation is.
And so basically we write those series out and then
yeah,
plug in the x
you just know, yeah, sine is x minus x cubed over 3 factorial, blah, 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 and yeah, you can write these out. And you're basically going to use them to approximate something, which means you're only going to use a finite number of terms, and then the very next term will tell you how good the approximation is. By the way, Taylor series also have an approximation theorem, but that's in the next section. It's not really in our syllabus, but the error for a Taylor series is given by the remainder term. It's always less than or equal to the, oddly enough, it's sort of the same idea as the alternating series approximation theorem. The n plus first term approximates the first n terms of a Taylor series. C has to be inside the interval of consideration, a random number, but it's the maximum number. C gives the max derivative on the interval. Right? So the n plus first term also can approximate a Taylor series, so you can actually use something very similar to the approximation theorem. Except figuring out this C can be kind of annoying sometimes, but if it can be done, you can do it, and you can figure out how good your approximation is. But yeah, the review for the test is already online, so you can try that. And on the final review, I asked you to do all the Taylor series problems from the past finals anyway. So you'll do those, and if you have trouble, you can see me in the tutoring center. The tutoring center is open during finals week, so I'll be there to answer your questions. And probably next week, I can give you your test back next week and just pick it up from me at some point. The final is on the 21st, I think. I put it in the syllabus. The room, I actually know the room number now. That's probably important. Should write that down. It's in this building. It's on the first floor. So it's December 21, which is 9 plus 10. In NAC 1203. So it's on the first floor. Like when you come through the entrance, you go to your left, it's one of those rooms way down on the left. Make sure you know how to find it before the day of the final. December of 21 from 1 p.m. to 3:15. Right, so usually the final would look similar to the format that you have online. So you'll be doing roughly 9 problems in an hour in 2 hours and 15 minutes. So roughly 15 minutes per problem is what you should be aiming at. If I were you, I'd try to practice to be able to do each problem in under 10 minutes. So you have time to do it. I'll be sending seat assignments for that final because we're with another class, so I'll have to tell you guys where to sit. But I'll email that at a later point. But that's where it's going to be. Tomorrow's class, I'm thinking that we shouldn't meet in the lab. Friday, tomorrow's what? December 11th? Class meets in Marshak 418S. In the lab, there's not enough space to give you the test. That actually happens to be the tutoring center so for those of you who've never been there, now you'll know where it is. I'll probably send an email reminder about that. So yeah, and with that, peace. No, I'm out. Finish the syllabus with a whole day to spare. I'm so happy. I'd like to thank my mom and my dad, everyone who supported me. And I thank the academy this meeting. Yeah, we're done. We're done. That's everything. This is everything for Calc 3. We're not totally done though. I have something for you to do. For what? The exam tomorrow is short. We have surveys, so you can tell everyone how much you love me. So this is your opportunity to tell the world. The exam is like half an hour. It's not a big deal. I'm actually like, it's the size of 2 problems. It's just series convergence. I put some of the Taylor series on it, but it's bonus. So if you get it, fine. If you don't, you have another week. The Taylor series.
It's not gonna be like that, right?
It'll probably be like the example final problem.
Okay.
Like one of those guys. Yeah, so I need a student volunteer to actually collect these and bring it to the instructions are here. Who wants to volunteer?
Is it second floor?
The location. You don't want to pass those around.